Okay, so yeah, hi everyone. My name is Shije Zhou, and I'm currently a final year PhD student at UCLA, the University of California, Los Angeles. And thanks for the attendees for waiting until the end. I'm very excited to share something really interesting to you here today. So today I'm going to talk about the eye-specific paper we published this year called the VLM4D towards the spatial temporal awareness in the vision language models. This is a joint work with the Microsoft and the UCSC and the USC. So I'm going to start with this video. So after watching this video, I would like to ask you a very simple question. From the camera perspective, what direction are the cyclists move toward? So I think as a human being, we are it's very easy for us to answer that they are moving towards the left. But let's see how the GPT-4o answers this question. So the GPT-4o says, considering the observations, if the cyclists were moving to the left from the camera perspective, they would get closer to the left edge of the frames. If the cyclists were moving to the right from the camera's perspective, they would move toward to the right edge of the frames, which is what we observe. Therefore, the final answer is right. And another SOTA VLM, the multi-model language model, Gemini 2.5 Pro, let's see how its response. So by comparing the cyclist positions from the start of the video to the end, it's clear that they are traveling from the left side of the screen towards the right side. So their movement across the frame is consistently in one direction. Therefore, the answer is right. So obviously, they are wrong because they're actually moving towards the left. So let's say another example. From the camera perspective, if I ask you what direction this car is moving. So I believe everybody will say this is moved to the right because as a human being, when we reason in space plus the time, which means when we do the reasoning in 4D space, we basically have a reconstruction stage in our mind that the global scene, the global world is operating like this. So we have kind of the global context like this in our mind. So it's very easy for us to reason that the car is moving to the right, no matter where it's located at every frame, at every time step. However, for the large language model or the large multi-model language model, or vision language model recently, I think the feature is extracted from the 2D space only. And so we can imagine that the transformer firstly petrify the RGB input like as a token, and also aggregate the features along the time axis to do this kind of the video understanding task or the 4D reasoning task. However, it is really problematic, as I just showed you just now in the two simple examples. So to try to benchmark this phenomenon, there's no such kind of a data set or benchmark to study this kind of research question. And we kind of have done the first one called the VLM4D benchmark. So what we are doing here is that we first collect some data. This data set, because there are many kinds of videos in the world. This data set includes both real videos and as well as a synthetic video. Synthetic video means the generative video from the video gen model, like the Cosmos. And because the VLM itself is very hard to answer this kind of question correctly, so we manually annotate some question and answer in the QA pair for this kind of tasks. And for the synthetic data, we have the video gen model, which we can control the motion of the object moving inside, but it may also make mistakes. So we also do the human evaluation pass on it. So we have done the human in the loop quality review to make sure this benchmark has the high quality, and we eventually have the VLM4D benchmark, and using the VLM like the advanced reasoning model like the GPT O3 to play as the LLM as the judge to kind of evaluate the result. So here is a glance of how the data or the question look like in our data set. So every question is kind of the multiple choice problems. In terms of the video sources, there are 300 extracentric videos in the real data in the real video. So which means it is object centric and the third person perspective video. And there are also 300 egocentric video, which means the first person perspective video like this. And also 400 synthetic videos, which is generated from the Cosmos in our case. And we also annotated 445 questions regarding the generative videos. So we have a kind of very good diversity in the like a video. Also, we have in total like 1,000 videos and over 1,800 questions in this benchmark. So now, so here's the statistics of this data set. So we have quite a balanced video resource in our data set. And regarding the real world data, we have around 55% of the translational question, 19% of rotational questions, 17% the counting question, and 9% false positive questions. So now let me show you what they are. So let's look at the first example. So if I ask you what direction is the horse in the foreground moving towards, the question should be right. So this is basically the extracentric translational motion question regarding the motion. And let's see the second example. Now, let me ask you, how's the jet ski rotating? So the correct question should be clockwise. So in this case, this is the extracentric rotational motion question. So notice that every question cannot be answered by just a glance of one frame of the video, and also you should have the spatial concept. So that's what we call the spatiotemporal awareness, spatiotemporal reasoning in 4D space. So the third question, is the cat turning to the left or right from its own perspective? So the correct answer should be the left. And this kind of question is not just simply from our like observers perspective, but to test the VLM spatial temporal reasoning from different perspectives, as long as it has the actual spatial temporal reasoning ability. So there are some example from the real world video and in extracentric perspective. So let's see some example in egocentric perspective. So this question is asked, what direction does the person move the couplet from its original position? So we can observe that this person moved to the right. Yeah, so this is a question classified as the egocentric translational motion question. And this one, what direction does the person turn to pick up the branch? We can see that it's turned to his right. And this is kind of egocentric rotational motion question. And another one. See, this guy turned to the right once. Yeah, so I'm asking you how many times does this person look to the right before turning? It should be once. And this is an egocentric counting question. So here the counting question we annotated in our benchmark is not simply counting like inside the frame, but it should have some spatial temporal concept behind this like counting question. Okay, so here we show the quality of our synthetic data set, a synthetic video using the Cosmos to generate. Yeah, so this is quite normal. This sports car moved to the right, and this is regarded as a synthetic directional motion question. And the second one, we see that actually this battle robot does not move at all, but just simply the camera pose is changing. So the correct question should be the not moving. So this is a bit challenging for the VLMs, and in this case we can generate it from our video GM model easily to challenge the VLMs. And the final one, let's see. There is an ambulance, but I'm asking you, which direction did the dog move? So obviously there's no dog there, and we call this kind of question as a false positive question that tests the VLM's critical thinking. False positive question here means that we query something does not happen at all in the video. So we want to just test that to make sure that the VLM does not hallucinate during its reasoning process. And it must truly understand the scene and give the correct answer. So yeah, so as we see that every question should be very, very easy to ask human beings. And we have some user study, and we find that for the human performance, in our benchmark, it will achieve like almost 100%. Here is a 98.8% accuracy for all the question in our in this benchmark. However, we find that even the very advanced the VLMs, the multimodal LLM model recently. So this is the best one is the Gemini 2.5 Pro model. It can only achieve the 62% accuracy on this benchmark. And we also classify the VLMs into like open source image VLMs, which means it can only like use the image multi-frame images as the input modality. And we also test the video VLMs, which can directly input the video file for the input. And we find that yeah, the accuracy is far away from the human performance. So this could be an issue. So one question naturally comes up is why VLMs don't work well. So the first thing we would like to consider about is that does the like reasoning process cause some problem here? So we do a simple experiment. We apply the chain of thoughts on the reasoning of each question, and we compare it to the direct output. So basically, we ask the model directly output the A, B, C, D, which option they would like to choose in the multiple choice question, and do not provide any like reasoning process. And we find that in this case, the COT, the chain of thoughts, does not help at all, which is also noted in the another early work called the thinking space in the CVPR 2025 for the 3D reasoning paper. So in the spatial reasoning or the spatiotemporal reasoning, the chain of thought often produce the flawed or inconsistent logic, and which reveal a gap between the visual and the linguistic knowledge. And we observe that even the chain of thought is a bit lower than the direct output accuracy. So yeah, so there's another reason is that we study the video SFT datasets, and we find that labels regarding the spatial temporal labels and the descriptors, they are problematic. Let's see one example in the shared GPT-4o dataset. So in this case, so basically shared GPT-4o dataset is kind of like very common used video supervised fine-tuned datasets, and it is annotated using the like GPT-4o, which is intrinsically problematic with this with this issue, with the spatial temporal awareness issue. So we studied the descriptors like directional descriptor, translational descriptor, rotational descriptor, and rotational action perspective descriptors. We find that usually their caption itself is incorrect. And we also study this kind of descriptors, and we find that so you can see the percentage here. So this means that if one descriptor is classified as translational actions, and for example here, for example here is classified as a rotational descriptor. Both rotational descriptor and translational descriptor, there is only 0.6% in the dataset. So we find that currently SFT video dataset lack reliable spatial temporal labels, and only less than 10% of detected motion descriptor were accurate. So what's the solution? This is a very serious issue, but what is the solution? We have explored some solutions. So in our paper, so the first one could be the most intuitive and most straightforward solution, is that using our dataset to do the supervised fine tuning here. So yeah, so let's see. We used two models, two open source video LLM as the base model to do this comparison. We used the Queen 2VL. 7B version and the Queen 2.5 VL 7B version. So the best model achieved this kind of number, and we fine tune with our dataset using the both real videos. The R here stands for the real video, S here stands for the synthetic video, and we find that using the full set of our dataset to fine tune this task, it will improve a little bit, not significantly resolve this kind of problem, but improved. However, it can only can achieve the around 55% accuracy on this benchmark. So yeah, so we still realize there's a far way to go using just kind of this data-driven solution. And the second solution we would like to explore is that why not we also establish a reconstruction stage for the VLMs. So we try to somehow force the vision language model to think as our human beings. Like we want to try to inject the global context. So what is happening globally to the VLMs, and then ask them the question. So what we're doing here is that, for example, the input video is like this. At every time step, we can only see the one frame and a partial view of the whole scene. So we do the 4D reconstruction using so basically using the feature 4X, which is published in the CVPR 25, which is another paper of mine actually. So we want to basically lift the vision feature space from the 2D to 4D through the explicit 4D feature field reconstruction. So why we want to do that? Because so the 4D scene reconstruction itself from the monocular video itself is kind of very hard problem. And we see that even in this case, even we have a very good visualization for the global scene. And it also will introduce some artifacts here. But if we also do it on the latent space itself and ask the VLM to inference from the latent space directly, the rendering artifacts will be bypassed. So we don't want to bring the trouble, and we want to help the VLM to inject the global context. So let's see the improvement here. So yeah, we see that this is a model based on this is an experiment based on the test model InterVideo 2. So we apply the chain of thought response, and we see that if the input modality is the original 2D video, it's around 36% accuracy, And if we input the left hand side one, the global view input, so basically you can imagine that you have a God view of the whole thing, and you can see everything at once at any time step. It's even like decreased. But if you use the like global feature field and you inference from this kind of reconstructed 4D feature space, it improve a little bit. And for the directional, the direct output response, it also improved. But there's a huge disadvantage of this kind of solution is that reconstructing the 4D fields itself is time consuming. So in our case, every like 5 to 10 seconds video will cost us like 40 minutes to reconstruct a 4D thing. So in this case, this is not a solution to like scale up. We cannot build this stage inside. This is not a feed-forward manner reconstructing stage. So it cannot. This solution cannot be scaled up, and this is just like a parsing optimization. So in a word, in conclusion, this direction towards the 4D reasoning ability of this VLM is still like an open question, I think, in our research community. And finally, if you have any further question, please feel free to visit the website of this page and feel free to contact me. And yeah, so this is the paper, the ICC paper I would like to share today. Thank you so much for listening.